and it is about clinical cohort data. So within the UGLI consortium, there are a couple of cohorts that have data on only cases. So, for instance, the Dupuytren's cohort, which was already mentioned by Harold, and also others that have participated in the UGLI consortium with only case data. And these cases have also been genotyped on with a GSA platform. GSA platform in Rotterdam. So, and these cohorts, they want to use lifelines as controls in their GWAS. So the issue is that they have to merge their data with lifelines. So there is a good chance that there will be batch effects when you merge the data. And so how can you control or limit these batch effects? So we developed a strategy where we want to do the genotype calling and the quality control of the clinical cohort, similar to lifelines. Then do the imputation also using the Zanger imputation server with the haplotype reference consortium, just like lifelines did with their data. Then the next step would be to check the overlap within lifelines, duplicates. Within lifeline, no, not within lifelines, between lifelines and the clinical cohort data. So check for duplicates. Are there? There might be samples that have participated both in lifelines and in your case cohort. But also relatives. So if, for instance, a father of a case participated in lifelines, also that one should be identified, and then ideally those should be removed from lifelines. If you don't want to remove any of your cases, but lifelines is big enough, so remove those from those duplicates and relatives from the lifelines data set. Then on this combined, on the combined data set, so lifelines plus your clinical cohort, you have to recalculate your principal components. That can be done using the genotype data, not the imputed data. And of course, in last step is to combine the imputed data sets for analysis. So the first step, which I mentioned, was the genotype calling. You want to do that as similar as possible to lifelines. Well, lifelines, they used OptiCall. That's a software for genotype calling, which is a software package that is better suited to call low frequent alleles than which is then the standard Illumina calling algorithm. These the OptiCall uses the raw data, or that can be extracted from IDAT files. So that's raw data of probe intensities. So that's for each of the alleles in the lab, there is a probe, and on this probe there is this a fluorescent label. So what is measured is how much do you see of the blue, let's say blue fluorescence, that's for the, let's say for the A allele, and how much do you see for red fluorescence for the, let's say for the C allele. I think, I have a slide over here with how such a intensity plot looks like. So here is a combined data intensity plot for both Dupuytren's and the lifelines. Here you see the intensity of one probe and the intensity on the other probe. It's on the y-axis, and what you ideally would like to see is 3 clusters. So here is a cluster that have no fluorescence intensity for one probe, do have for another. So these are homozygotes for the one allele. These are heterozygotes, and these are the homozygotes for the other allele. So that's also this is combined Dupuytren's and Lifelines. Here is Lifelines separately and Dupuytren's separately, and these are the genotypes as called by optical. So you clearly see that, well, there are 3 clusters: the CCs, the CTs, and the ETs, and this is a SNP that is well scored in both Lifelines and in the Dupuytren's cohort. This is what you would like to see. So the problem with this is that, well, before you can apply optical to these raw data files, you first have to convert the data to this optical format. And what we recently figured out is that the best strategy is to combine these raw data before calling, combine the clinical cohort data with, well, at least part of UGLI. UGLI itself is too large to call them in one batch. So what we did is we took one batch of UGLI and combined this batch of 1,200 samples, UGLI samples, with data from the clinical cohort from the Dupuytren's, and then did the calling on that simultaneously. So this was an example of a good SNP. So then after the calling, you extract again the data from only your clinical cohort, and we perform quality control on the data, similar to what was done in UGLI, except for a couple of changes. Because we want the data to be as similar as possible to UGLI, we first extracted only those SNP that passed the UGLI QC. So they were considered of good quality. Then we performed a Hardy-Weinberg check, and this Hardy-Weinberg check was more lenient than in UGLI itself, because we deal here with a case cohort, so it might be that Hardy-Weinberg equilibrium is violated because they are cases. Skipping this entire step resulted still in too many false positive hits. So we thought, okay, we just put a more lenient threshold for it. Then in Lifelines, they did a minor allele frequency comparison with genomes to see if there's the minor allele frequency in your cohort should not be that different from the Caucasians in the 1,000 genomes, because with the same ethnicity. But of course, if in the clinical cohort you're interested in differences with controls, so it could be that an allele SNP has a different frequency in your cases because it's a case cohort. So we skipped this check and we added a new check where we already on genotype level combined the data with UGLI and filtered out SNPs that were highly significant. And again, you would think, okay, but then you throw away your significant results. That might be. But if that's the case, we found that this is more likely to be caused by different genotyping assay failures than by true causal hits. And the idea is that genotyping assay errors will, if they are there, then they will not affect the genotyping assays on nearby SNPs that are in high linkage disequilibrium with them. So when you do impute then again this SNP that you at first filtered out and you impute it again, the idea is that you then still will get you're at least sure that it's not due to batch effects. Any questions on the quality control steps that we suggest to do in a case cohort? If not, guess not. So, okay, then after your data has been cleaned, then you want to impute it, and similar to what Lifelines did, we imputed it using the Sanger imputation server. There's also the Michigan imputation server, which works a little bit, has has a nicer user interface than Sanger, but it does give a different different results. So to avoid batch effects, also use the Sanger imputation server for your imputation. And because of this imputation, well, in Sanger, the Sanger imputation server likes the SNPs to be aligned to the positive strands, and to make sure that this is the case, there is a tool by the McCarthy lab called HRC BIM check, which checks if your markers are aligned aligned correctly and if the alleles are correct. And with this check, if you run this check, then without this check, the Sanger imputation server will give some errors and say, okay, your SNPs are not aligned correctly. I see, for instance, a C and a T, but in my data, what Sanger expects to have what is it, A and a G. So this is the final check before submitting it to the Sanger imputation server. And another thing is that the Sanger imputation server likes to have VCF files, and the quality control is done with Plink. So also a final step with Plink is to convert your data from the binary Plink formats to VCF files. Then Sanger imputation server will also give you back VCF files, and then you have to combine your Lifelines data with your clinical cohort data, and that's very easily done with this VCF tools merge command. It takes some time, but it's not that difficult. And then, well, after combining the data, the VCF files, you of course want to run your GWAS. So one thing to notice is that likely your sample size in your clinical cohort will be much, much smaller than that of Lifelines. So it's good, as Robert also mentioned in his presentation, if you have a high case to control ratio, that might introduce false positive results. So it would be good and efficient to sample unrelated individuals from Lifelines. And then you need to exclude from Lifelines, well, the related individuals from Lifelines itself, which you identify with this determined independent individual script that you worked on in the practical session. Also, you need to remove the overlap and related individuals with the clinical cohort. And you may want to exclude others from lifelines, maybe because they are cases themselves, or because they have they use medication, or they have some other conditions that are not acceptable for a control. Or maybe you want to restrict on age. In the previous session, I think there was a question, I think by Cynthia, if you would like to restrict your data for age. Esteban suggested to have a sensitivity analysis, but most diseases occur with higher age. So if you have your controls higher age, only in a higher age range, I think that's fine. But you may bias against low chance of mortality, for instance. So then, because we advise to use only unrelated individuals, you could use Blink for the analysis. But the limitation of Blink is that I find that there is only limited information in the outputs that Blink gives. So there's another package, Sniptest, that also could be used. You can download Sniptest and upload it to your account. It doesn't require installation. It's a standalone program. So that's its advantage. It gives you much more information in the output, the results file, including, for instance, minor allele frequency and imputation quality, which is lacking from the Blink files sometimes. Advantage of Sniptest is also that files need not, so the files of the clinical cohort and those of lifelines, not necessarily need to be merged. You can Blink of a Sniptest can handle if you give it 2 different files, but then be aware that you have to harmonize the SNP IDs before your analysis. And with this BCF tools merge, then your SNP IDs, there will be a check on SNP IDs before producing the output file of the combined data set. And then after you have run your GWAS, you have, of course, to check for batch effects, because although we tried everything with our QC and joint calling to avoid batch effects, but still there might be batch effects. So check how many significant results you find, and if you think this number is way too high, then there is still something wrong. What you also do is look in the literature, for instance, in the GWAS catalog, and find out which SNPs were identified at an earlier paper, earlier study, and check what the significance is in your study, or vice versa. Check which significant results you find in your study and check if they match with those from literature. We would also advise you to run a QC after GWAS on the results of your GWAS study. And we developed a package called GWAS Inspector. Alireza Ani wrote this package, and we also submitted a paper to bioinformatics, which is nearly accepted. And then one of the things that you find when running the GWAS inspector is the genomic control lambda, which Robert was also talking about. And he suggested a threshold of 1.5, but it depends on whether you do it. If you have a trait or a disease phenotype, and if you have a trait, so a continuous phenotype, then I would say a value of 1.1 is an indication that there is a high potential for batch effects. So if you encounter either a too high number of significant results, or if your significant results don't match with the literature, or if you see this high genomic control lambda, then you should look into the data, the raw data, or at least genotyped data, to see why these batch effects occur. And you may be able to identify the causes. Maybe there are a lot of minor, very rare allele, very rare SNPs that are causing this. Then you may be able to filter your final GWAS results and have a good data set left. So if you filter on, for instance, minor allele frequencies less than 1%, or imputation quality less than 0.8, then you may end up with a good, valid GWAS file. But if that's not the case, then you should dive into your data to find out and see if you can find out why or how you can solve the batch effects. So as Harold also this morning said, we thought it would be easy to merge the data, but that appeared not to be the case. And we are still working on this pipeline. We're still trying to optimize the quality control pipeline for clinical cohorts, but still, yeah, I think we are nearly there. So we have, as I said, we have been applying this to Dupuytren's disease, and we did it first without the joint calling of, so genotyping calling of Dupuytren's and lifelines. And then we found many significant SNPs and a high genomic control lambda. And now that we did the joint calling, the number of significant hits reduced up to only 1/3. And this lambda was within an acceptable range. Nevertheless, I did still spot an error in the pipeline this morning, so I'm rerunning now the imputation for the Dupuytren's cohort, and hope to find and do the merging again, and hope to find an even smaller number of significant SNPs, and that better match with those from literature. Okay, any questions on this? No, then I would like to go to my roundup and to have some final remarks and important notes. So it is important to note that, well, as mentioned already a couple of times, that within the UGLI GSA data, there are many related individuals, and also within the CytoSNP data, there are relatives. So you have to account for these relationships within your analysis and do it. As we did this afternoon, better use this mixed model analysis using SAGE, and the genetics department developed a nice and efficient script for this, so this is easy to use. So I would advise to go for SAGE GDS for your GWAS analysis. Also, there is overlap between the UGLI GSA and the CytoSNP data. So if you would want to analyze both sets, then it is important to remove the overlap between the overlapping samples, and then preferably you remove them from the CytoSNP data, because that's the worst chip with a less dense map of SNPs. But in addition, you not only the overlap, also relatives between the data sets need to be removed, because, yeah, as I said, if you have twins, then and you have, for instance, one twin in the GSA that was genotyped with the GSA SNP, and another of the twins was genotyped with the CytoSNP data. These are highly related to each other and will bias the results if you combine the data using meta-analysis. So also the relatives between the data sets should be removed, and again, preferably from the CytoSNP data. So we have to determine the overlap and relatedness both within, not within, between the data sets, between the GSA and the CytoSNP data, because as we said before, it's not preferred, advised to combine the data and analyze them together. So you have to determine the overlap and relatedness. Well, we already did that for the complete data set, so full lists are available and can be shared with you. But it might be that you already want to remove individuals from either data set because you don't have phenotypic data on them, for instance, and then it's better to use the scripts on this new data, on the subset of data. Then that's most efficient. And as I said, remove your individuals, preferably from the CytoSNP data set. Well, and some issues that you will encounter when analyzing your data is that the SNP IDs may be different between files, either between case and lifelines cohorts, or between your own the genotype data and GWAS summary statistics when wanting to calculate polygenic risk scores. So you have to harmonize SNP IDs, and then the chromosome position format is preferred, but then you might end up with duplicated SNPs based on only these chromosome and position, and add alleles to the SNP ID, but that makes it even more difficult to harmonize. Then finally, I would like to get feedback from you if you missed anything in this course, or did you think that some parts were superfluous? Did you see some errors in the exercises or answers, or do you have suggestions for improvement? Therefore, I will send you an evaluation form next week by mail, and I would like you to fill that in and return it to me. I will get the answers of your evaluations from the system. Okay, then if you have, I can imagine that you could still have questions on the Lifelines phenotypes. If that's the case, then address your questions to the Lifelines data management team, data@lifelines.nl. If you have questions on the cluster software, or if things or also, let me say, also if you need access, so it might be that you in the chat I got questions on I don't have access to the CytoSNP data, or I don't have access to the genotype data. If you would like to get access to data and also address contact the Lifelines data management team. If you have other questions on the cluster, so for software or well, issues with your jobs, then well, there is this website on the Gearshift that may help you, and otherwise contact the GCC, the Genomic Coordination Center help desk. And finally, if you have questions on genetic data analysis, you can approach us, Harold or me, for any help. So maybe, for instance, for this polygenic risk course, then we would be happy to help you. Okay, and with that, I like to thank you for participating, and hope you enjoyed it and learned a lot from it. And well, I wish you good luck in your further research and with your Lifelines plans. Okay. Yes, Roja.
Yes, I want to do the polygenic risk score both in the Cytotype and also the GSA dataset. So can I combine the polygenic risk score directly in the analyze?
Oh, that's a good question. So you want to calculate on both chips the polygenic risk scores and then do an analysis. I think that could work, yeah. But then I would suggest to standardize your polygenic risk scores within each of the two cohorts.
Okay.
Then combine it and add the cohort as a covariate in your analysis.
Okay, nice to know. And another question that we adjust for the relatedness in the dataset. Does it mean that we take the family ID as a random effect in the analysis?
You mean also for the polygenic risk score analysis?
Yes. Yes.
It's also a good question. Yeah, in fact, what we now do in the phenotypic data analysis, we actually don't take into account the family relationship, but that's actually, I think, should also be taken into account. So, but also if you have polygenic risk scores, you should adjust for the genetic relationship between individuals. And yeah, to only take the family idea is, I think, a bit yeah, short-sighted maybe, because yeah, some families are very large. But yeah, at this moment, I'm not aware of other ways how to do it. But at this moment, that might be the best way. Yeah.
Okay, thank you.
Okay. Well, if there's no other questions, then well, again, thank you and good luck, and then see you maybe some at other courses or other other research. Okay, bye.
Thank you. Bye.
Bye.